In lesson 2.4, the chain rule, we're going to learn about differentiating a composition of functions. Now, you've learned about composition of functions in the past. It's essentially where one function is contained within another function. For example, consider the quantity 2x squared to the fourth power. That would be a composition of function. We have 2x squared on the inside, and that whole thing is to the fourth power. It's a function within a function. And how do we differentiate something like that? Well, the secret to that is, in fact, the chain rule. So that's what we'll be looking at in this lesson. However, before we get into any of the notes, let's take a look at that example that I just gave to you. So, given the function quantity 2x squared to the fourth power, you might think that we could simply apply the power rule to this. Drop the exponent in front, and if we do that, we'll get 4 times the quantity 2x squared to the third power. Well, just for the sake of showing you what's going on here, let's go ahead and multiply this out real quick. And if we do that, we'll get 32x to the sixth power. I'm going to caution you that this is not correct, so don't write this down in your notes at all. Because what if we were to simplify this first and then differentiate? Hopefully you would agree with me that our original problem and this new problem, which will say 16x to the eighth, are equivalent. All I simply did was did quantity 2x squared to the fourth power, got this. Now, if we differentiate 16x to the eighth, what's going to happen? Well, 16 times 8, that's going to give us, I'm going to do this wrong probably, 124, I hope. 124x to the seventh power. And clearly, these are not the same. So something went wrong. I will tell you that this is the correct answer if we go about doing everything right. So what went wrong here? What went wrong is that we actually have a composition of functions, so we can't go using basic differentiation rules. What we're actually going to need to use is this thing called the chain rule. So let me go ahead and explain to you what the chain rule is. To do the chain rule, you do differentiate the outside part of the function. That was the part that said to the fourth power in our example. However, you then need to follow it up by differentiating the inside part of the function. So it would actually look like this. In other words, if we think of this as f to some blob, then if we differentiate that with respect to x, what we'll actually get is f prime of blob, but then multiply that by the derivative of the blob. Would that really make a difference here? Well, let's go ahead and take a look. If I start by beginning with my original problem, which was the derivative of quantity 2x squared to the fourth, well, let's see here. The outside part of my function is to the fourth power. We can consider this to be the blob. So if we differentiate the outside part, we do get what we thought we were going to get originally. However, we then need to multiply that by the derivative of the blob. And remember that the blob is 2x squared, so we'll need to multiply by 4x. Now, if we simplify this out, this will give us 32x squared times 4x. And if we simplify that, we're going to end up where we want to end up, with 128x to the seventh, simply because this 2 should be a 6, of course. So that's how we get the correct answer. We're going to need to use the chain rule whenever we have a composition of functions. Just always think there's a blob on the inside. So take care of the outside first, and then we'll take care of the blob on the inside. If you want to see a general power rule, if you don't like all this f and g and all that stuff, if we have a function to the nth power, all we need to do is go n times the function to the n minus 1. Well, that's the power rule. But then we need to multiply that by the derivative of u. And there is our general power rule, which is actually what we did here. So now that we've seen how this works out, and you've seen the chain rule right there, and you've seen the general power rule, let's go ahead and try a few actual examples, and we'll start with example A, of course. In example A, we're going to try to differentiate this function here. Now, first glance, you might not say this needs the chain rule. Where's the composition of functions? This simply looks like a product rule problem. Well, as soon as we start differentiating, I think you'll see where the composition of functions is happening. Well, let's take a look. If we're going to do this, of course, f prime of x, we will need to use the product rule. So I'll start by keeping the first term intact. Of course, it doesn't really matter which way you do it. Addition is commutative. But there's our first term. If we differentiate this term, of course, the 3 will come out front. We'll be left with 2x plus 1 squared. But then remember the chain rule. Remember the chain rule. This right here was actually a blob to the third power. And what's the derivative of this blob? Well, that's just a 2. Doesn't seem like that big of a deal, just a 2, but it will make a big difference later on. So there's the first part of our product rule. The second part of our product rule will differentiate the first part, and we'll leave the second part intact. That's the blob to the third power. So fantastic. If you want to go ahead and multiply all this out and simplify and do all that good stuff, certainly be my guest. I'm going to make the observation that both of our terms here have a 2x plus 1 squared in them. This one right here, you can see 2x plus 1 squared. This has 2x plus 1 cubed, so I'm essentially just pulling 2 of those out. And when I do that, what am I left with? Well, here I'm left with, it appears the 3 and 2 give me a 6, and I have 6x squared minus 5. And when I pull a 2x plus 1 out of here, I'm left with my 12x, and I have a 2x plus 1 left over. So there's my factoring out of 2x squared plus 1. And if I want to carry it out one more step, again, this isn't necessary, but a lot of people like to do what they believe is a full simplification. So if we do that, you can try it yourself, of course. I tried it earlier, and I got this. And this is as simple as I feel like making this. I don't need to go any further. So you might have said to yourself, well, couldn't I have just multiplied the whole thing out before I began? I have a 2x plus 1 quantity cubed, so we can cube that binomial. That's not too big of a deal. And then we can multiply it by this 6x squared minus 5 and get this big, ugly, nasty polynomial. It looks like it might be to the 5th power. And then we can go through and differentiate that. Well, you could. You certainly could. You would get the same answer, although it might look a little different because this is factored. But you would get the same answer, and that's fully acceptable. But I'm going to argue that in this particular case, using the product rule, even with the chain rule, is easier than simplifying at the beginning. Of course, as I said, it's all up to you. However, in example B, you'll find that simplification is not always an option. Let's take a look at that one now. So example B might look kind of easy, and in fact, I'm going to posit it is. But I want you to try this one before we try it together. Clearly, as I said, there's nothing you can do to simplify this. But do you see the composition of functions? Can you identify the inside function and the outside function? If you can, that's a good step towards getting started on this. If not, it might help you to rewrite this as sine theta to the 1/2 power. Now do you see the inside and outside part? I hope you do. The sine theta is of course going to be the blob of this problem, if you will. And if we want to differentiate, all we're really going to need to do is drop the exponent. And so we'll have 1/2 blob to the negative 1/2 power. And then all we'll need to do is just differentiate the blob. So nothing too difficult here. If we fill in our pieces, of course blob is just sine theta, and we'll take that to the negative 1/2 power. But what is the derivative of the blob, or the derivative of sine theta, if you will? Of course, as you know, that's cosine theta. So there's our final answer, 1/2 sine theta to the negative 1/2 power times cosine theta. Now again, you might be one of those people who likes it a little bit simpler than that, so we can certainly accommodate you. We'll have cosine theta over 2 times the square root of sine theta, and it's not going to get any easier than that. So there you go, not too difficult of a problem, but just be sure that you can identify the inside and the outside part of any composition of functions. Well, before we move on to example C, let me encourage you to jump ahead and try example C. It looks a lot like B, so give it a shot. Pause the video now. When you come back, we'll get started. In example C, the big surprise is that there are actually two blobs that are present. Can you identify them by looking at this? Do you see the two blobs? Well, if I rewrite this as the sine of 2 theta all to the 1/2 power, maybe that will help you see how sine of 2 theta is one blob, and the simple 2 theta part is another blob. That 2 theta itself is a blob. So what's going to happen when we differentiate this? It's not going to be any more difficult. It's just going to be a little bit more drawn out. But what we're going to have is 1/2 times the blob, which of course has the other blob inside it, and that will be to the negative 1/2 power. We'll need to multiply that by the derivative of this blob, which of course has the blob inside of it. And then finally, we'll need to multiply that by the derivative of the small blob. So we're basically peeling the onion back. We have to the 1/2 power. That's the outermost function. Then we have a sine. That's kind of the middle function. And then we have that 2 theta. That's the inner function. So that's where each of these pieces is going to come from. Let's see if it really makes it that difficult. This will be 1/2 times sine of 2 theta to the negative 1/2 power. No big deal there. This, if we do this blob differentiated, that will just give us the cosine of 2 theta. And then if we do the derivative of the inside blob, that will just give us a 2. So putting all of it together, it looks like we're just going to end up with the cosine of 2 theta over the square root of the sine of 2 theta. So just introducing that 2 into the argument of the sine actually does change our answer quite a bit. But just be careful when you're using the chain rule. It doesn't just have to be one inside function. There could be many functions inside of each one, kind of an inception kind of deal. So always be on the lookout for that. And now that we've done that, let's combine our chain rule with a quotient rule, because the quotient rule is something we absolutely love. So with that, let's take a look at example E. Example E is a problem that I think you will find to be fun and exciting. Certainly, I hope you can identify the inside and outside portions of this function. And so if we want to differentiate this, we'll start by looking at the outside. We'll have 3/2 multiplied by the blob, which in this case is 2x over quantity x plus 1, and that will be to the 1/2 power. That completes the power rule for the outside function. But what about the inside function? Well, for that, to differentiate 2x over x plus 1, looks like we're going to have to use the quotient rule. But at least it's not that bad. If we do the denominator multiplied by the derivative of the numerator, subtracted by the numerator times the derivative of the denominator, and just divide that by the denominator squared, we should get something that looks like this. Now this numerator looks kind of ugly, but if you do a little bit of math, I think what you'll come to find out is that all of this up here is actually just equal to 2. So what is that going to do for us overall? Well, it looks like we're going to have 3/2 times the square root. I'll go ahead and put the square root on. 2x over quantity x plus 1. And then this function is simply going to be 2 over the quantity x plus 1 squared. Of course, we could simplify that down just a little bit more if we realize that the 2 and the 2 cancel, and if we realize that we have x plus 1's in both of our denominators. It looks like what's going to happen is we'll end up with 3 times the square root of quantity 2x divided by the quantity x plus 1 to the 5/2 power. We have a 2 here, and of course this would be to the 1/2 power, giving us 5/2 overall. So there's a beautiful example of having to use the chain rule, which is actually a quotient rule inside of a power rule. Isn't it beautiful? With that, let's take a look at our last example, example F, where I get to expose you to a true AP-like kind of question. In example F, it's not a quick, just do it and be done kind of thing like the rest of these examples. We're actually going to have to work it out analytically and then plug in values at the end to get our result. It's a fun one, so let's take a look at it now. So before we begin example F, I do need to tell you that this is the kind of problem that I love. And it's the kind of problem that you'll be dealing with a lot as we go throughout our studies of calculus. Also, on the AP exam, the writers love problems like these as well. Because you can't just plug in numbers and see what you get. You actually have to know what you're doing. We'll have to do this problem analytically, and when we're finished, then we can plug 3's into everything to see what our final result is. But in essence, all this problem is saying is we need to differentiate this function. So, that being said, let's go ahead and begin. To differentiate this function, I'm hoping you can identify the inner part, or the blob, and the outer part, which is simply that exponent. So to do the chain rule, well, I'll start by just differentiating the outer part. Well, that means just dropping the 2 down, writing what I have left on the inside, which itself is kind of ugly. And then it'll be all that to the first power, which I'm not even going to write to the first power. But then, because of the chain rule, we now need to differentiate the blob. Differentiate this ugly quotient thing. So to do that, let's first do the denominator times the derivative of the numerator. Well, here's my denominator, no big deal. And here is my derivative of the numerator. So that part was okay. But then I'm going to need to subtract the numerator times the denominator. The numerator times the derivative of the denominator. That might be a challenge. Let's see. Here's our numerator, or our high, or top if you like. So no problem there. But to differentiate the denominator, I have another chain rule in effect. Notice that k is my inside portion, my blob if you will, and h is the outside part. So to do this, I'll just do the derivative of h, keeping the k on the inside, and I'll follow that up with the derivative of the inside, which is k. And I have all that. Don't forget, with the quotient rule, we need to divide by the square of the denominator, which in this case will look like that. Alright, so good times. There's our derivative. Hope you enjoyed that. That was a lot of fun. Now it's going to be even more fun, because what we need to do is we need to replace each of those x's with a 3. And if we do that, let's see what's going to happen here. 2 times, well, g of 3, according to the table that we have, is just 6. So we'll have a 6 on the top. H of k of 3. And k of 3, again, we can use the table. K of 3 is just 3. Alright, fantastic. That takes care of that part. Now let's look at this. Here we have h of k of x again. We're already familiar with that. That was the same as the denominator here. And then we have g prime of 3. Well, g prime of 3 is given right here. That's just going to be 2. Do you see how much fun this is? All we had to do was just do the derivative, and now we're just having a lot of fun plugging in numbers. Good times. So we'll have 6 times h prime of k of 3, which remember k of 3 we said was 3, times k prime of 3. And that's given to us here as 9. So there is our numerator. In our denominator, we'll simply have h of 3 quantity squared. So, good times, good times. This is a lot of fun. Let's go ahead and continue working this out. 2 is going to stay the same, but here I'll end up with 6 over h of 3. And h of 3 is given as negative 1. Now that's kind of nice, because that's something I can actually work with. If we take a look at all this, h of 3, that's given as negative 1 again. And we'll multiply that by 2. And then we'll subtract 6 times h prime of 3. h prime of 3 is given up here as 1. And then we have that 9 hanging out. And of course, in the denominator, we have h of 3 squared. Now, be very careful here. H of 3 is given to us as negative 1. But interestingly, h of 3 quantity squared is given to us as 28. You might ask, how is that logically possible? How could we square negative 1 to get 28? that's not the case. And in truth, although it is a valid question how that could happen, it's irrelevant to this problem. If they tell us that h of 3 quantity squared is 28, then it is, and that's what we must use. So be very careful on that. Now, this is a big mess of stuff. I'm going to encourage you to go ahead and simplify it all you like. It's not a difficult simplification to do, but we've reached the point now where I'm just going to jump ahead and say that the result would simply be 24. Yes, the rate of change of f of x when x equals 3 is 24. That would be the slope of the tangent line. That's all we're finding out here. So, that was a really fun problem, and we've learned a lot this lesson. We saw how when we have a composition of functions, we can't just differentiate those using our basic derivative rules. We actually need to apply the chain rule. And remember, with the chain rule, all we need to do is differentiate the outer part of the function and then multiply that by the derivative of the inner part of the function. We also learned the general power rule, which is really just a general version of the chain rule. It's not really that important. If you know the chain rule, you're good to go. So we did a few examples of those. We intermixed the chain rule with product rules and quotient rules, saw how everything meshed together quite nicely, and then did an AP style problem that required you to analytically differentiate a function before you could plug in numbers. So with all that being said, good luck on your homework tonight.